text me or so.
Good morning, everybody.
Good morning.
What's happening tomorrow?
Yeah.
Right? An exam on things where you're like, it's simple, I can do the math, but I can't set it up right. Right? So between now and tomorrow, you want to get from the guessing stage to the applying knowledge stage, right? Okay? And hopefully you've been working through that. Before we get there, though, I did want to, we had a science show on Friday. It was great. We had a good time. Miss Cherry and Miss Willis. I know them by their first names. I never call them by their last names, so I can never remember. Did a fantastic job. Okay, and from pictures captured by our very own Jeff Winters. He's not here right now, right? Okay. We had a good time, and there was this one picture that he grabbed. Now, I do want you to know he's obeying the rule of thirds. Okay, he's got a nice depth of field effect going on here. Right? Okay, very well done. Right? Okay. So we were setting up for this thermite demonstration, and during the demonstration we couldn't get it to light, and so we finally lit it manually, and then I went in to put this cone on top of the thing, and that happened. Right? And there's Jeff. Okay, these are Jeff's pictures, right? Okay, and Jeff snapped this one right here. Now, a lot of people were really worried for my safety. I was touched, right, by the number of people that came up, and the Physics 4C students didn't, but the other students did. Okay, and said, "Are you okay?" Because this went up in my face, and it's hard to tell here, but I had already started moving backwards when this thing started happening, and so I was a good 3 feet from it. And a few sparks got on me, but I didn't lose any eyebrows. But I saw this picture. Jeff sent me this picture. I was like, wow, that's a great picture. And so, of course, the first thing that jumped into my head was, right? Right? Okay. So it's like the Balrog coming out of the, right? Okay. And for those of you who don't know what the Balrog is, right? Okay. It's the mythical demon from the Lord of the Rings. Okay. And Gandalf standing on the bridge saying, "Thou shalt not pass." Right?
I came this close to making an edit with it with the wizard hat.
With the wizard hat, yeah. Okay. So yeah, that's where my so golly, more than 10 years ago, my students in my 4C class made up a T-shirt that had this picture. It was that actual picture on the T-shirt, and they put a bunch of physics equations on there, and they then photoshopped my face onto the Balrog's face, right? And then put down Physics 4C, you shall not pass, right? Okay, or something like that. Maybe there should be a Mr. Balogh merch store. That's the thing. I don't want to make money off of that. No. Yeah, I could, but then I gotta anyway. Yes, giving it to charity would be fantastic, but then there's the logistics of having to do all that, and I didn't have enough time to put diagrams together for you guys for review. So, but I did have time to put it all in.
Maybe you could use it to get the school in physics to put it out.
Yeah, that becomes really tricky, believe it or not.
Yeah.
Go figure, government gets in the way.
Yeah.
Right?
They get in the way, right?
So, yeah. I thought about it, but maybe, actually we do have something, Crystal. Yeah. Science and Engineering Club could do it.
What?
That's true.
Right? I could release my image.
Still t-shirts.
Yeah, looking
People will buy that. I'll do the Photoshop. I'll put it on a t-shirt. You can Photoshop.
Oh! All right. The other thought is I hate my face out there. Because I know my face is the face of nightmares for many thousands of people that have taken physics at Fresno City College.
Probably.
All right, let's review. So, just very quickly, any questions about what these topics are trying to say?
What is pointing vector RHR?
Okay, pointing vector right-hand rule.
Oh.
I'm asking you to do a right-hand rule to tell me the direction of electromagnetic wave.
Oh,
Okay? So, by way of example, okay? If the magnetic field is going that way and the electric field is going that way, then what direction is the pointing vector going? The pointing vector's direction is given by the cross product of E and B, right? E cross B. So you would do finger in E, rotate for other finger in B, and the thumb is pointing into the board, right? Okay. All right. So what if E were this way and B was coming out of the board? What direction would the pointing vector now be? E, B, and so the pointing vector S would be down. What if the electromagnetic wave were traveling this direction and the electric field were pointed out of the board? What direction is the magnetic field? So now we know that S has to be, our thumb has to point in the direction of the pointing vector. Okay? Our finger has to point out of the board. So that leaves only one direction left for B, right? Should be sort of that way.
Yeah.
Right?
Which finger is which on this?
So in cross product, the first one is always your pointer. The second one, the second vector in the cross product is always your middle finger. And the result of the thing you're finding is your thumb. So I'm asking you to be honest with you, I put this on in the exam hoping it would be a gimme, easy. You've done right-hand rules before, okay, in 4A and in 4B. So, and we did it together in here in 4C when I talked about the pointing vector in the direction. So just practice. It's a cross product. Do the right-hand rule for a cross product. You've got it. The question is conceptual in nature because it's right-hand rule. So it's just like it's going to be in or out or left or right or up or down, right? So we were given that the pointing vector is pointing this way. So that's your thumb, right? The electric field is pointing out of the board. So I know that my thumb has to be in the direction of S, my finger has to be in the direction of E. That only leaves one direction for my middle finger. These are all harder than the one I gave you on the exam. I say that now and you get to do it. Any other questions on the topics, just for clarifying the topics?
The Rayleigh criterion.
Rayleigh criterion is resolution, so dots per inch on a computer screen or a telescope's angular resolution, like how far apart do different objects have to be in order to be able to see them. So we did this. This is what we did last Wednesday.
Was there a formula?
Yeah, Rayleigh's criterion. 1.22 lambda over d. Yeah.
So even though the RH we just talked about, the right-hand rule,
Mhm.
doesn't stay conceptual?
It is conceptual because the right hand rule is always conceptual.
That's what I'm.
Yeah.
There's 3 conceptual questions?
Sure. There's 12 conceptual questions. It just happens that 3 of them have a multiple guess answer.
Is polarization hiding up there?
Hiding? I mean, polarization is always lurking in the wings. But is it explicit here? No. No polarization. I thought about it. And then I gave you the right-hand rule question instead.
Thank you.
Thank me later. Yeah.
What is the light wave one?
The what?
Light waves?
Light waves conceptual. So this is, what do you know about light? And so I did the whole sort of history of light. Don't panic, I'm not going to ask any dates. Right? But how do you know that light is a wave? What are the 2 things only light does?
Interferes.
Interference
And diffraction.
and diffraction. So, was there an experiment we talked about that shows the interference of light waves? The double slit.
And the
So light waves conceptual is in that vein of what is a light wave, right? It's a wave in the electric and magnetic field. Okay, how do you know it's a wave and not just a particle? Well, you had Thomas Young, right? And I don't think I asked you like any names of people. Now I'm worried. I haven't looked at the exam in like 2 weeks. So I don't remember.
On your sheet.
But right, like Thomas Young did the double slit, right? Showing it, right? What did Newton think light was?
Particle.
He thought it was a particle. Like if you know that, you're good. Okay. What happens to light when it goes into a material that's not a vacuum?
Slows down.
It slows down. Okay. We talked about dispersion. What's dispersion?
Just kind of shoots off all
It's when white light encounters, right, and there's different speeds of light depending on its frequency, right? And so red light doesn't bend as much as blue light, right? And it disperses, it spreads out into its rainbow of colors. What's scattering? When a light wave encounters a particle, gets absorbed, and then re-emitted in random direction. Okay? So a rainbow is the result of dispersion in raindrops, not scattering. Okay? It's the result of reflections off of this rainbow. So there's a lot of conceptual framework for how light behaves and interacts with objects. And so that idea, okay, of light, and I know you don't like the conceptual questions because I can never be very specific about them. Because if I'm specific about them, it totally gives away what the question is, right? So I am asking you, and I always ask you, you know me. It's concept first, and then we apply the math, right? To bring the physics together. The concept should be informing you of everything. So this question is going to be a variation on the theme of dispersion, right? Refraction, what's going on, etc. Lots of topics that we covered.
So for objects, do we need to know what type of people, if they have stigmatism?
For corrective optics, nearsightedness and farsightedness. So the corrective optics conceptual question can cover things like astigmatism, right, where you know that the focal length horizontally and vertically are different. We'll be about that. But like it's a pure conceptual question on how do you correct somebody's vision, like what's going on. Okay? So no, say for like a nearsighted person, right? What is like, I shouldn't say stuff like this. What's broken in a nearsighted person's vision?
Nearsighted, they
Yeah.
can see far away.
They can't see far away, right? So it's their far point where they have a problem, right? And meaning that when you make an image, when you put glasses on their face, where are you putting the image of distant objects?
They can see.
Where they can see, which is their far point. For a nearsighted person, it's all about the far point. Always, the image we're putting at the far point. For a far-sighted person, what do they have an issue with? What's broken? Their near point is broken. Their near point is not standard. So where do you want to put the image for things that they're trying to hold close to their face? At whatever their near point is. So the conceptual question is grounded in those concepts of corrective optics. Same question, Jaming, or different?
I'm going to provide the sheet that you said.
The sign convention sheet? I guess I can.
We still have to commemorate it. I put it up.
No. I will print out new ones. You will have the sign convention sheet that I provided in class with you on the exam. And if I forget, I'll put it on the screen. But you will have a copy of the sign convention. Okay? So you don't have to worry. I mean, you're going to want to review them anyway, right? So, but I'll provide you a copy so that you can have more room on your cheat sheet for whatever it is.
You go over the question box?
Yeah, we will. I just wanted to make sure we understand what the questions ask, what these topics are about.
So is there ever going to be asked like what's the maximum memory angle?
For
Diffraction.
like diffraction gratings?
Yeah.
Diffraction grating is on there. So the answer is yes. Could be. It's whatever the diffraction grating question is. It's got a grating in it and diffraction's happening. That's what I remember.
How do you answer that? Do you just keep plugging in M values?
Well, you can't go further than 90 degrees. So yeah. All right. So let's get into specific about topics.
It's about the eyesight thing, corrective.
Yeah, what about it?
Which one is the one that goes behind the retina and which one goes in front of the retina?
That doesn't matter that actually doesn't matter. Yeah. The answer is that nearsighted people, it forms in front of their retina.
Before?
Yeah.
Okay.
Nearsighted people, their eye focuses too much. That's why they can't see far away. And the opposite is true for farsighted person. But that's actually less important than knowing where to put the image so that they can see it. All right. Ali asked me a question about what are all the pictures, right? For like all the diagrams for optics, and I had started going through looking for all the different, and I sort of like grabbed screenshots, and I never got a chance to like put them together in any way, shape, or form, right? Okay, but I found like these pictures. Okay, okay, so these aren't in any particular order, it looks like. Take me too long to order them. 1, 2, 3, 4, 5. Why is there only 5 here? Oh, because it already opened the other one. Okay, so what are the 6 pictures that you might want? Now, I didn't put any like image distance or anything on these pictures, okay? But we can go ahead and maybe label them right now, okay? So the object, where do you always put the object distance? Where's it measured from?
The object.
It's measured from the vertex of the system, right, where the optical axis crosses the plane of the optic, okay? And then goes to wherever the object is. How do I know this is the object? It's where all the rays are coming from, right? All 3 of these rays are coming from the tip of that object. Now, this is the case where you have an object inside the focal length of a converging lens, right? So the image distance is always measured how? From the vertex to wherever the image is, right? So image distance in this picture would be right here. And this picture stays the same wherever you put that object as long as it stays inside the focal length. You can go to the applet, the online applet, and see the picture change. Yeah, like the actual size of the image and stuff and where it's located changes. But the actual lines don't really change, right? They all make a virtual image. And the image distance is always negative because it's on the same side as the object, etc., etc. So this picture covers all the cases for when an object is inside the focal length of a converging lens. All right? This is a diverging lens. Okay? And again, sorry it's so small. It just is the way it is. Okay? Object distance right there, image distance right there, and it doesn't matter for a diverging lens whether you're inside or outside the focal length, you're always going to get this setup.
Isn't the object
Yes. Sorry. I was going too fast. DD. There we go. Okay. So you're always going to get this virtual image. It's going to be reduced. It's going to have a negative image distance because the virtual image forms on the same side of the lens. And blah 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 blah. Okay. And again, this is the only picture you need for a diverging lens. It covers all the cases. The details will change a little bit, but you'll always get the virtual blah blah blah. Okay. So that's converging lens and diverging lens. Here's a mirror. We missed one of the converging lens pictures. Where is it? Right there. That was.
So basically, the mirroring we need all these diagrams for the different situations is more for the real or virtual, right?
It's a tool for you. If you just trust the equations to give you everything, you're fine. But a lot of you have told me, oh, we want the visual picture, right? I want something to anchor my brain in because I like the pictures. I always draw a quick sketch when I'm doing optics problems because if I don't, I'm going to make a sign error. I guarantee it. I don't make sign errors when I draw the picture because I can see which side is the front and the back, and it doesn't matter which way the rays are going. If the image is on the same side as the object, I know I've got to get a minus sign. So for me, it helps, and for several of you, you've asked for these pictures, so here they are. Now, object distance, right here, image distance, right there, and is this image distance going to be positive or negative?
Positive.
By the sign conventions, you'll end up with a positive image distance for this set. So this is a converging lens when the object is outside the focal point. And again, for anywhere outside the focal point, you're going to have a very similar picture. So this one picture captures all the possibilities for outside until you get to infinity. When you're at infinity, you got parallel rays. So where's the image going to form? At the focal point of the lens. But that's the definition of focal point. So 3 pictures for lenses, right? You got the converging lens with object outside focal point. You got converging lens of object inside focal point, and then you have a diverging lens. And those 3 pictures cover all of the cases for a single lens system. Did I see a hand? No? Okay. Then we get into mirrors. What?
I wrote a question, but sorry about that. This is a converging lens, is it correct?
Yes.
And then so if the image, so then the focal length, if it's in the front, the object distance in the front, wouldn't it make the object distance negative for the image?
Object distance is always positive because the front side of the lens is always
for the image would it not be negative?
here the image distance is positive. Look at your sign conventions. When the image is on the back side of the lens, it's a positive. Yes, and here's one of the big mistakes that people make is they learn the mirror ones and think the mirror ones are the same for lenses, and they're not. How easy is it going to be to make a sign error on this test?
Extremely.
Very easy. Am I going to give you any partial credit if you do? No. Because that's a physics sign error, right? It's not a math sign error. All right, and when it comes to mirrors, you've got 2 kinds of mirrors. Spherical mirrors, you got, what kind is this? Concave. And then the other one's convex, so concave where it's bending towards. So if you have an object outside the focal length, you have this setup. If you have an object inside the focal length, yeah, that, I need to, sorry, for completeness. Let's see here. This is my object distance. I'm drawing them up there. Really, they're measured from the vertex, right? I'm just drawing them up so that they're clear. And object distance is positive here. What would image distance be here?
Positive.
Positive, because for mirrors, when you're on the front side of the mirror, you give positive image distance. And then we have, when we have the concave mirror, but we're inside the focal length, object distance image distance. So the image distance here, positive or negative? Negative, because the image is forming on the back side of the mirror. And then the other possibility is the convex mirror. And this picture applies for every convex mirror. No matter where the object is in relation to the mirror, you'll always get this arrangement of rays. So I captured all of those on the iPad. They'll all be on the PDF, right, that I upload from today's class, right? So you can go replicate them, print them out, edit them out, do whatever you burn them. Totally up to you. Ali, did I answer your question? Okay.
Weren't there also some graphs from Corrective that kind of had good detail to them?
I have what?
Like a good amount of detail to them?
Well, yeah, they're more detailed than the ones that I just kind of drew there. But yeah.
Are they on the recording?
Yeah. Both on YouTube and in the PDF. At least they're supposed to be. Nobody's complained yet. Which means nobody's looking at them. Or
Not true.
They will tonight.
Margaret.
Is there a telescope question?
Okay, so I don't. So telescope. Is there one on the homework?
Yeah, I don't think there is.
No.
So where do we get the example from? Is it the lab we did? But you didn't do it.
Wasn't there one on the homework?
Not a telescope.
Not find the length of a telescope. Didn't I tell you about the problem? Focal, they gave you focal length of object, focal length of eyepiece, find the magnification. No. Okay, then lab. Did a whole lab on it. Yeah. So, and you guys probably don't have those labs, do you? Because you're good for nothing. Physics teachers probably forgot to give them back. Yeah, I can tell because man, these are thick. Oh, I know. There's the interferometry lab also in there. Other questions? Elijah.
For those pictures you just showed, it's not even in the picture, right? Those just are
I decided this time to not teach you how to draw ray tracing diagrams nor require them in any way, shape, or form.
Are we still going over
Go over corrective optics. What do you mean?
the sign of, you just can't mix it with the far side.
Okay, I understand, but I don't understand why this is confusing. Like I get it confused in my brain too, and I have to kind of stop and think about it. But in summary, a nearsighted person, okay? What's the problem? The far point is not at infinity. So normal. Don't judge anybody, right? But a normal far point is infinity, meaning people can focus on objects that are infinitely far away from their face, right? And what's the near point? 25 centimeters by definition. It's sort of like the closest that most people hold stuff to their face and it's comfortable. Okay? So the problem for a nearsighted person is that the far point is not infinity. It's less than infinity. Okay? And so what's the furthest from their face that they can focus on something? Their far point. So where do you put the image distance? At the far point, right? But because the setup is eyeball, lens, object, and where is the object located? The objects are at infinity. The image is going to form at their far point, so by definition and convention, the image distance will be what sign? A negative image distance. Why is it negative? It's on the front of the lens. Both the object and the image are forming on the same side as of the lens. So if object distance is positive, that makes image distance negative. What kind of image is it? It's a virtual image. Is it upright or inverted? It's upright. Okay? And whether it's enlarged or reduced kind of depends on the setup. That's it. There really are there's no like tricks here. That's just straight up nearsighted people have a problem with their far point. And so a lens what you got to get out of your brain, I know why part of what you're confused, but you got to get out of your brain is that eyeglasses somehow change how the eye works. That is not what happens. Okay? Corrective optics, meaning eyeglasses or contact lenses, they produce a new image for that person's eye to focus on. We're not changing their eyeball. You change their eyeball when you do LASIK. There you're actually physically altering the vision system. All right. For farsightedness, what's the problem? The near point is greater than 25 centimeters, right? Okay. So distance to the image. Where are we going to put the image that we're forming from the lens that we put on their eyes? We're going to put it at the near point of the person, okay? Not the standard near point. So what's the object distance? The object distance is 25 centimeters. We want to put an object at a normal near point, but produce an image at the near point where they can actually see it. By the way, what's the object distance? I kind of implied it up here, but didn't write it down. How far away are objects for farsighted people or nearsighted people? Infinity. Yeah, it's infinity. All right. So, in the drawing, where we have the eyeball, the lens, okay, and we have an object, okay, at 25 centimeters, and we're forming an image, again, on the same side of the lens as the object, the image distance will be what sign? Okay, and it'll be equal to the negative of the person's near point. So if their near point is 1.2 meters, right, the image distance will be negative 1.2 meters, or 120 centimeters. Watch your units, right? No, don't mix units. You don't always work in centimeters, always work in meters, always work in light years. Be consistent with whatever unit you're using. Okay? The light years was a joke. That starts Wednesday. Let's see. Do I have everything in summary here? I mean, you probably want to flesh out more around the idea, but those are the essentials of corrective optics. Just don't guess. Right? Get to a point where you're not having to guess. Which one's which? Rely on, this is practically definitional, right? It's defined. Nearsightedness as defined as a far point that doesn't work, you know. Question 9 on chapter, this current chapter? 33. The answer to that might be no. This happens when Wiley Plus is having a problem on the back end. And it's usually not fixed.
I think I wrote the whole.
Does anybody have a copy of the problem?
Yeah, I got it.
That's a database error in Wiley Plus. Okay, so this is the optical fiber one, Bradley. Okay, and we're having to do total internal reflection. So I'm gonna kind of make up. What was exactly they're asking me? What is the value of theta for total internal reflection? Thank you for being so diligent and copying those things into your notes. You guys are awesome. All right. So the problem was, here's an optical fiber. Optical axis. And an array of light was like coming in and bouncing off, right? And we want like total internal reflection here, right? But it came in at like a different angle. So here's theta 1. Here's theta 2, and I think they were asking what does theta 1, what's theta 1, like what's the angle that the light has to enter the fiber in order that all subsequent bounces will be at the critical angle, so it stays inside the fiber. All right, so that means that we've got to draw normal here, okay, and we need to find so right here, this is the critical angle, isn't it? The angle of incidence up against the normal. And what's the relationship between theta 2 and theta critical? I have a triangle, right? Where I have theta 2 right here and I have theta c up here. It's 90 minus theta 2, isn't it? So the critical angle, 90 minus theta 2. Or in other words, theta 2 is 90 minus the critical angle. Because did they give us the indices of refraction?
Yeah.
Yeah, okay. So how do you find the critical angle for total internal reflection?
Inverse sine.
Inverse sine of what?
And lower.
You always take n low divided by n high. I taught you this, right? It's not theta 1 or theta 2 because I get confused. I don't understand what that means, right? Which one's 1, which one's 2, blah, 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 blah. For the critical angle to happen, you must be in a material of higher index and trying to get into a material of lower index. It does not happen the other way around. And so total internal reflection can only happen when the ratio of that inverse sine is less than 1. Which means it has to be the lower index divided by the higher index. So I just always remember it as low divided by high.
Random size tangent, but do we need to write down refraction if they're in water?
No. I'll give them to you, but they're 1 and 1.33. Glass is 1.52. Diamond is 2.4 something something. Air is 1.00021. I used to know the indices of refraction of like 30 of the elements on the periodic table. because we were trying all these mirror coatings, making like, I did this refraction of uranium, silicon, we had nickel, we did iron, we did platinum, we did ruthenium. Yeah, indices of refractions of all these things in the extreme ultraviolet portion of the spectrum. That's where we specialized in all that data for that.
Did you do any with lab-made elements or no?
They're not stable is the problem. So no. We did yttrium, that was interesting. We were gonna do beryllium, but then decided to not do beryllium because when you blow beryllium up into its constituent atoms and deposit it on surfaces, you get something called beryliosis if you breathe it in. Beryliosis is like black lung disease that the coal miners would get. Only with the coal miners, you had to go down and work in a mine for like 6 months to have an elevated chance. And with beryllium, all you need is like a single exposure in the parts per trillion concentrations. And you can start getting, it's called beryliosis. Your lungs begin to dissolve. So we were like, no, not going to even play with that. When the space shuttle used to land, space shuttle would land and it would be 40 minutes before anybody was allowed to open the hatch or even approach the space shuttle. Not because it was cooling off, but because they had to use beryllium in the brake pads. And they wanted to make sure the beryllium dust had dispersed enough before anybody approached to be able to open the hatch. Anyway, beryllium bad. Where was I? It's Brian's fault. He asked me a tangential question, so my brain did a tangent. Oh yeah, critical angle. So we would calculate the critical angle here, and then it becomes a geometry problem, right? We'd figure out what theta 2 has to be, and then what's the relationship between theta 1 and theta 2? Snail'S Law. We know theta 2, we know N2, we know N1 was air. Solve for that angle. Did I answer your question, Bradley? Sorry, I don't have the numbers to work it out. Other questions? See, I'm answering questions you didn't even know you had, like about beryllium. I went to Lawrence Berkeley National Labs where they did have a system for you working with beryllium, and you had to operate it externally with like big glove boxes and robot, like joystick controls for the robots and stuff. Yeah, so glad I didn't have to work with beryllium.
I prefer the 3D metal printers that they have like
Yeah,
Arizona State.
all right.
Better than working with beryllium.
So with beryllium and with uranium, when you're working with uranium, so uranium was the other one we're having trouble with because we used uranium in the end. It was our perfect thing, but basically we had to like do all the radiation exposure stuff, and uranium will give you the equivalent of lead poisoning, but with way less exposure. So like lead, you practically have to like eat it to get lead poisoning, but with uranium, all you had to do was breathe the dust in, and you basically had lead poisoning. Had to be careful there. Explains a lot, doesn't it?
Uranium catches on fire too.
Oh yeah, that's good stuff.
Can you go over for diffraction grading relationship between
So when it comes to diffraction gratings, let's see, this is from memory, so it's going to be dangerous. It's d sine theta equals m lambda, right?
Yes.
Okay. And m is the order of is the order number for the full pattern. Right? Complete replications of the diffraction pattern. And For diffraction grating, better write this down, diffraction grating, okay? Theta is not small. Everywhere else we can use that small angle approximation, but when it comes to diffraction gratings, we can't. Okay? Now, I'm sorry, Anthony, what was your question?
So I was just wondering what because in the homework sometimes they give us a length and they give us the amount of rulings.
Oh, right, okay, right. So the ruling of a diffraction grating is the number of lines per length, usually given in lines per centimeter. But I think in one of your homework problems, they told you something like there was 7,000 lines in a 23 millimeter distance, right? So to find the ruling of this grating, you take 7,000 and divide by 23 times 10 to the minus 3 meters, right? To get your lines per meter. Right? Now often they're given in lines per centimeter. So usually you want to take that to lines per meter. Be careful with your conversion. And then how does the ruling relate to D? You just invert it. D is the separation. It's the distance between lines, or the distance per line. Distance of separation between lines. So if you know the ruling of a grating, you know the distance between the lines on it, and vice versa. Did that answer your question, Anthony?
Yeah. Also, is it also true if we know the entire length of the grating, then the number of rollings times the distance between them is also just that length?
Yes. I would say if you know the if you know, okay, yeah, you're fine. Yes, go that way. Yeah, because you can just take the lines per length and multiply by the length of the ruling, and now you know the total number of rulings. I know it's confusing. We use the word rulings to indicate lines per length, but also like just the total number of lines, because we really don't have another way to talk about the number of lines.
Yeah, for resolution, the Rayleigh criterion, will you give us that number? And we can talk about like the 1.22 for n equals 1. So.
That's the only one you need to know.
Okay. 1.22.
1.22 lambda over d. It's the only one I remember.
Okay.
The others aren't very interesting. You don't do shouldn't say that. All the people that do optical physics Rayleigh's criterion just died. But there isn't that many interesting physical phenomenon that go on with the other orders in that pattern. All the meat is down there when the first maxima overlaps with the first minima of the other pattern.
Can you go over question 2 on chapter 36?
Maybe not if Wiley Plus is having trouble. Is it chapter 36? I've seen this problem before. I was convinced it was my browser rendering engine that was having trouble, and it turned out that Wiley wasn't even serving up the information. You say problem 2?
Yeah.
Can we have a copy of it? See, students come to the rescue. Alright, lines of diffraction grading, lines of the same order appear at the same angles. You know, we're getting really into Inception here. But I had to take a picture of the screen.
Oh, he's not. Why are you working on mobile?
It's working on mobile,
Yeah.
so maybe it is my browser.
It's not showing the, you said for number, what number is that one? Oh, okay, it is showing the picture.
That was interesting. Why did it reload?
Oh,
I wonder if it's cached on your phone, because I just tried even just using a VPN to get off the school's network and still won't. I'm pretty sure, like I looked into the code that the page was rendering and it's just blank. There's nothing there. The server's not serving up the correct thing, so.
I don't know, usually my VPN like breaks stuff.
Oh, where'd it go? Right there. Okay, so here's the question, okay? A and B, same wavelength, and the lines are the same order, appear the same as A and B. Okay. Line are the same, lines are the same. So what's the picture B? That must be for a different question, okay? Which grading has the greater number of rulings? A, is it capital A and capital B they're doing?
Yeah.
Okay. So in the diffraction grading equation, right? Do you see how in B the pattern is like, I don't know, wider? See how narrow the lines are in A, and then they kind of like, they're fatter in second picture, capital B. So this angle, right, depends on the relationship between order number, wavelength, and the rulings of the gradient. So when we solve for this angle, inverse sine of m lambda over d, this angle theta, in order for it to be big, this argument has to be close to 1, right? Right? Because sine of 1 would be 90, right? And as we go down and make this closer to 0, this would get closer to 0. So, which of these has the greater number? When you have a bigger number in the denominator, what kind of number does this become? A small number, right? If it's a small number, what's your angle going to be? Small, meaning that the width of those patterns is going to be smaller, right? The angle describes like sort of how spread out those patterns are. And so, which one has the greater number of rulings? It's got to be A. It's got the tighter lines in it. Was that the answer? The one with the greater number of rulings is A?
Yeah.
Yeah? Okay. What was the next part of the question? Okay, so the second figure B, single diffraction grading of 2 wavelengths, which lines A or B, the left or right, or the word with the greater M. Okay, so in that second picture over there, they're providing two different wavelengths. And they want to know, right or left, which one has the greater M value. So, different wavelengths, same D, right? How do we get bigger angles? The bigger M value, right? So the question is, in that picture, which of that has a bigger angle, and how do you know? Bigger theta. The bigger the theta, the more sort of spread out the pattern is. So the ones on the left are the ones with the bigger M values. Again, bigger angle, more spread out pattern. In other words, think of it like subtending, like when we talk about telescopes, right? And that you have a bigger angle where the pattern begins and ends. And if we like in the first part, if we tighten up, right, the diffraction gradient, the number of rulings, that angle gets tighter. So as the light hits it and the white light gets spread in the rainbow, if you've got lots of if you got smaller D, it'll just be this tighter picture. And if it's a bigger D, it'll like spread out. And that's just following the math of this relationship. Can we keep going?
Yeah.
Is the center of the diffraction pattern located to the left or the right in figure A? It's going to be on the left. How do I know it's on the left? In other words, where's the zeroth order in this picture? Wavelength, blue wavelengths. Big or small? Very small, right? Okay. Where's the blue? It's on the left. So that's a smaller angle than the reds, right? So the center has to be over to the left. The blue will be closest to the center. The reds will be further away. Again, just doing this, right?
How did you know about the width again? Sorry for the capital A and capital B.
Let's say light comes in and strikes this thing, right? The diffraction grating. And then it spreads out, okay? And it subtends an angle. You can find where the sort of center of the next order is. But remember, that order looks like a sort of a spread out pattern. And so there's going to be a theta that's measured for like the blue side of the spectrum. And then there's going to be a different theta for the red side. Like a diffraction pattern naturally spreads out. It's not a singular value. And so what I'm looking at is I'm trying to relate the spread based on wavelength, right? Okay? And see how far spread out the blues and the reds are. And in this second picture down here, this one right here, okay? There's more of a spread right here. That's a wider thing, right? Theta is bigger here. Okay? Here the theta is narrower. That was supposed to be narrow, not marrow. Theta small. Right? This question is really, do you know what an inverse sine function does to an angle? That's really what they're asking here. Because so far they've asked me to think about what happens if I change D. What happens if I change M. I'm guessing the next one is what happens when I change lambda. Oh, they did ask where is the diffraction grating, right? It's to the left. in those pictures over there. Was there another question after that? Or was that it?
So there's one more.
One more?
Same thing as the last one was for figure B.
For figure B? Okay, so here we've got two different wavelengths, if I remember correctly, same grading. So this was a little bit trickier. The smaller wavelength, okay, which corresponds to a smaller theta, is going to be the closest. So it's on the right. Is that correct?
Yeah.
The narrower lines, because the wavelengths are different, they're both red wavelengths, but because they're hitting the same grading, I'm keeping this the same, right? And the smaller the wavelength, the smaller the angle, therefore the closer you are to the zeroth. Because what's the angle for the zeroth always? When you put m equals 0 in here, what's the inverse sign of 0? 0, right? So the one with the narrower line, which is going to be narrower because the wavelength is smaller, is closest to the center of the gradient. Mr. Balogh, making it look easy since 1999. That's why I started teaching in graduate school. Does that count? Was that real teaching? No, it was fake teaching. Because I didn't have my degree. So I was just an imposter as a graduate student, right? I knew I picked the right career when the students secretly wanted me to teach instead of the professor that was actually in charge of the class. Not that he was a terrible person or anything, he was a physicist. So was I, but I specialized in how to talk to people. Physicists know how to talk to other physicists. Yeah, that's easy. Talking to other people, not so much. You're not wrong. This means we need more English majors in STEM, right?
English STEM, what would that even look like?
It's called STEAM. Have you heard about this?
Yeah.
So what does STEM stand for? Science, technology, engineering, mathematics. So what's STEAM?
Art.
Yeah, you add art into it. And believe me, we need to add the artists for more reason than one. They need help. The arts are struggling in terms of like funding and everything. Like there's like the number of English majors has dropped off precipitously in the last 2 decades. Like it was going up and then tank, right? And that's sad because language is beautiful. And English, for all of its flaws, does express a majority of the world's ideas, no matter which country you go to. So that's a loss. And so is music and dance and all of those other things that, quite frankly, make doing STEM worthwhile. You guys aren't answering any questions, and so I'm just going to start talking.
Did you give us a formula for path length?
Path length difference just depends on the situation, right? The path length difference for double slit is different than the path length difference for thin films. It's a concept. Thin film! Have you just given up on that one?
Yeah. That one was.
You just gonna flip a coin? Yes, draw it, set it up. How do you know when a light does a 180? Low to high transition, right? Okay. 2 nt equals m lambda and 2 nt equals m plus a half lambda are not frozen in stone in terms of what they mean in terms of constructive destructive, right? And the one way to do it is to just draw it and concept your way through it. You're welcome for only giving you one. Only one question, right? It's only listed once in the topics, right?
Yeah, I think everything once was
I was crying tears because I wanted to give you 12 questions on thin film, but I held back. Yes, I mean,
Could you go over the low tides because in the homeworks they gave like this to be what diffraction?
yeah, quite possibly. So give me a material, a thin film material, any material.
oil on water.
Oil on water would be easy. All right. What's the index of oil? Just make something up.
1.52.
That's glass. Make up something different.
1.43.
1.43? Okay. So there's the oil varies. It depends on the oil and some other things. Okay, so we have an index of 1.43. Then we have an index of what it's sitting on. Is it sitting on water? Okay, 1.33. And then we have the index of what's above the oil. Kind of a boring affair. All right. So there you go, Jumping, right? We've got 3 indices of refraction. And in the equations that we end up with, which index do you put in there? It's not a guess. What goes in for N? 1.43. Why? Because that's the film, right? The 2NT represents a path length difference. Right? Path length difference equals condition. And so the wavelength is changing in that film, so we're correcting for that wavelength change with the index of refraction. Do the 1 and the 1.33 matter? Yes. It's how you know if it flips or not, right? So, first bounce, flip or not?
Yeah.
Yes. Second bounce, flip or not? No. So, if we leave it alone, M lambda means leave it alone. If we leave it alone, what do we have? And if we add 180 to the second one? I knew this stuff on the day that I was taking my graduate level thin films class. Okay? And the teacher didn't show up. He was my graduate advisor. And he had a minor family emergency. He had to take his wife to the doctor or something like that. And he called the office, and the office came up to the room where we were all sitting, the 10 graduate students taking the class. And the secretary, who knew who I was for reasons that we won't talk about right now, came in and said, David, you need to teach the class. Dr. Allred says you're teaching today. Okay. No prep. Waltzed up to the board, started talking about, I knew which chapter we were on in our textbook, and started going. I don't think too many people failed that quiz, that test.
So thin lens as opposed to thin film.
What about it?
What's the difference?
One's a lens.
So same thing, different medium.
So thin lenses are about refraction. Okay, thin lenses are all about applying Snell's law. Thin films is all about interference and the relationship between the waves. So, and why are we keep using the word thin? We're making it easy on you. Because when the lens becomes thick, you actually have to do different algebra, different physics to account for the thickness of the lens. So when it's thin, you don't have to make those corrections. It just makes the learning of concepts a lot easier. For the telescope? What's the magnification of a telescope? I remember this as big part over little part.
Forgot the negative sign.
Okay, fine. Okay, so it's big part over little part because on a telescope you put the big lens in the front and you put the little lens on the back, right? The eyepiece is on the back, the objective's on the front, so you want your magnification to be as big as possible. Why is it when you turn a pair of binoculars around everything looks small? Because you inverted this equation, right? And so your magnification is smaller because you put the big number in the bottom. Okay? So magnification of a telescope, right, given by focal length objective over focal length eyepiece with the minus sign. Length of a telescope, also slam dunk. What's the length of a telescope? Yeah, it's the sum of the focal length. So of course, this is for a lens-based or refracting type telescope, which really, when I'm asking you to calculate anything, that's the kind of telescope it's going to be. We didn't do any of the calculations for Schmidt-Cassegrain or any of those.
No microscopes.
And microscope's not mentioned.
Okay.
I was choosing between, do I put a microscope, do I put a telescope? I decided to put a telescope.
Okay.
Because I like you and I like telescopes. I think that did answer your, more or less all of your questions. Telescopes are mentioned in Rayleigh's criterion, but you don't need to really know the optics of the telescope. You just need to know the diameter of the telescope to calculate its resolution. Anthony.
What was the equation where we like combine these two things together? It was like it's 25 centimeters times L.
That's for microscopes. It's for calculating the magnification of a microscope. Okay, microscopes are not mentioned, so.
This is for telescopes.
What about it?
So, if it works, why is the angle, is that perfect, or
We don't need that.
If the phase difference between any two rays is 180, that's destructive. So if I have a ray that's 180 and another one that's 0, what is it? Okay. If I have a ray that's 180 and the other one is 360, what is that? That is also destructive. Okay? If I have a ray, for whatever reason, is 720 and the other one's 360, what is that? That's constructive. What's the difference between these two? 360 degrees. That's constructive. So phase a relationship, the only time you have destructive is when the difference in angles is some value, some multiple of 180 degrees.
Just to make sure, when it's reflected, it has to be in a bigger angle and it has to come from high to
In refraction,
low. Yeah.
so if you're refracting and your light's going from a lower index to a higher index, the angle will be smaller.
When will it reflect that?
Total internal reflection?
Yeah.
That's when you're going from high to low. So if your light's traveling in a high index and it's trying to get into a lower index, that the angle of refraction will be greater than the angle of incidence. Snell's law.
Okay, that's-
And are we gonna have to use Brewster's law, or is that just?
No, I would have asked about polarization. I would have told you about polarization.
Okay. We just-
You've had me long enough to know that, I don't know if you've noticed at all during optics, how often do I reference my notes when I'm teaching? Like these equations,
Not very often.
they just come straight out of my head, don't they? You also know that I don't memorize very well at all. So what does that teach you about optics? I've done it a lot. Right? In order for these things to stick like that, it means I've done it a lot. Right? I can't usually remember Newton's second law without looking at it, right, on a page. So to be able to remember all of these optics things just means I did it a lot. And quite frankly, I really enjoyed it. Like, more than any other part of physics, optics. I just, for whatever reason, have always liked optics. From cameras to telescopes to electromagnetism and light waves. Ah, so good. All right, I will see you tomorrow. Now, wait a second before you go. Do not miss Wednesday. Do not think you can miss Wednesday just because you took an exam. I have to begin to rewrite your understanding of the universe on Wednesday. Do not miss it.
First day after the exam is the most important. Is that day, you're like, what's happening?